Hi, I'm going to talk about parallel computation, which is part of the R-Julia-MATLAB course as taught by NICE, and it is part of the advanced day, and it's the first session of that day. What I'm going to do, these are your learning outcomes that you can name and describe 3 types of parallel computation. You can explain at least one advantage of them. You can explain at least 2 disadvantages of parallel computation. And you can explain how to use your computational resources, that is your HPC power, effectively. I will start with this image because this shows already some type of parallelism. So here we see a robot. And here we see an extra head with cameras. So there's 2 heads and there's a gripper and there's an arm. And how this was programmed 20 years ago, I was a master's student with this project, is that each of these components, they had their own computer and they would send messages with what they were seeing to a main computer. And this was to give enough processing power for each process. And so these could all work independently, and it gives a very clean architecture because you get, like, the main computer gets all these messages in and has to work and works with that, and already the signal has been processed. Why parallel computing is important, especially in this course where we talk a lot about HPC clusters. Most HPC clusters, they use 7 to 10 days as a maximum duration for a job. Your calculation may take longer than that. And that's a problem. And there are multiple techniques to solve it, but one technique is to use parallel computing, where we use multiple CPU cores to work together on the same calculation. The idea is that if you have multiple things that are calculating, then the calculation is done faster because they work together, and then you can get this computing time to below 10 days. So to make sure we use the same terms here, I'm going to go through this diagram, going from big to small. What about HPC cluster architecture? So an HPC cluster is the unit we're working in this course, but instead I'm going to work with the smallest thing. So a core is something that does a calculation. And a core is part of a CPU, and each CPU there are 1 or more cores per CPU. A CPU, however, is a collection of cores that share the same memory. So all the cores share the same memory of that CPU. But there are 1 or more CPUs per node. So here we have a node, and this is usually what we talk about when we say login node. A login node, or a node, is a collection of CPUs that share again the same memory, as they can share the same memory. And an HPC cluster has 1 or more nodes, and typically many hundreds of them. An HPC cluster, that's the highest level here, then typically has a whole bunch of nodes, typically hundreds. And there is one or more HPC clusters per universe. The universe has a collection of HPC clusters, and there's only one universe for all practical reasons. So this terminology, usually I will be talking here about the core level. When I say core or thread or worker, these are terms I will use interchangeably. When I talk about multi-threading, I mean the process that enables more cores. I will mostly talk about the core level. There are multiple types of doing more things at the same time. I'm going to zoom in on this. So you can do multiple things at the same time in many more ways. One way is that you say, well, I'm not going to do it. Then it's called single-threaded. This means your calculation runs on the single core. And this is commonly what you do by default, especially if you run some kind of program. Sure, there are programs that don't do this by default because it's programmed like that, but this is like the basic start. This is where you start. You need to do work to not do this. However, you can go up one level. You can go up to the node level, where you say, all right, we're going to use a lot of cores together, and that is called thread parallelism. So these cores must be on the same node so that they can share the same memory, and then the node uses all its cores to run a calculation with a lot of cores. You can go up one step. You can say, all right, I'm going to use the whole HPC cluster, or you can use all computers in the universe, and then this is called distributed parallelism. This is when you send out messages to other nodes, to other HPC clusters, to other computers, and say, all right, you're going to do this, and let me know what comes out of it. And then you need to send messages around. This session is about thread parallelism. I think this is a good step, the first good step going up, because you do this at the moment you always work at the core level, and we're going to go one more step up to thread parallelism. And also today's session after this is about distributed parallelism, where we're going to step it up again. First we need to talk about when to use parallelism. Like, how optimal is it? What are there some disadvantages for this? Now, so I'm going to walk you through a calculation so that you get familiar with the terminology and how to think. So we're going to look at the effectiveness of parallelism, and effectiveness here is expressed in three different terms. You'll see soon. So parallel computing means that you spread a calculation over multiple things that can calculate. In this session, these are cores. At this moment here, I'll be talking about cores. I will be talking about things that can calculate together. They use the same memory. They're very close. That's what you need to know. So let's take a look at this calculation. Like, this is a very old argument I'm going to bring up. It's like 50 years old. So imagine a calculation that takes 16 time units represented as this. So here we see a representation of a calculation where red cannot be run in parallel, green can be run in parallel, and white is time spent doing nothing. We see that there are no white squares yet. We only see one calculation that takes 16 time units and runs 16 time units on one core. But there's a green section that we can parallelize. How it exactly goes is beyond this talk, but we're going to assume we can parallelize it. In my next session we're actually going to do it and see how it looks, but here we're going to go through the theoretical aspect of it. So of these 16 time units, we see that 4 of them cannot be run in parallel. You can imagine like loading a file and saving a file, making plots, making a plot. Sometimes you really need to do one thing, and you can't spread it out. And all programs have this feature that some sessions are parallel and some not. Some sessions cannot be made parallel. Alright, with this calculation it takes 16 time units. Now we're going to take a look what happens if we make this calculation parallel. This looks like this. We have 2 calculation units. In my case these are cores. And here we see again 16 squares, the same 16 squares that need to do work. But the green squares that can be run in parallel are spread out to be doing the same calculation. And we assume nothing extra going on here. So there will be overhead. In practice we assume there's no overhead. But we do see that suddenly there are white squares popping up. So that's because part of the calculation cannot be run in parallel. So that means that the other thing that calculates is doing nothing. However, it does take the calculation down from 16 time units, so that was from left to right in the big thing. This was 16 time units in total. So imagine 16 seconds. And when we run it on 2 cores like this, it turns into 10 time units, because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 time units! This means that the so-called speed up of using 2 workers is 1.6. It goes 1.6 times faster than before. If you want to see the details, it's in this paper where they for example introduce that term, where they define speed up as x is n times faster than y, exactly how I just phrased it. And here you can see a bit more details how I do that. But the mathematics is not important here, but it gives you a bit of an idea. However, we already seen in the second example that there are white squares. That means there are time that a core does nothing. So 4 of the calculation units are spent waiting. So we have theoretically 20 units of work that could be done. We know this is 10 times unit. We have 2 cores. So that means theoretically we could do 20 units of calculation, but 4 are spent waiting. We only do 16 units of calculation out of the 20 possible. So that means 80% of the calculation time is spent efficiently. You can also see a bit more details in this dropout box how I calculate this, but it should more intuitive sense. Here I'm going to extend these figures together with the calculation. I want to make it a bit bigger. Yeah, there. And I want to take you a look. So here we have 3 workers, 3 cores, 3 threads, 4 workers, 6 workers. I'm going to take a look at the speed up. Because with 1 worker or 1 core, it takes 16 time units. With 2, 10. With 3, 8. With 4, only 7. And with 6, 6 time units. So that means that we can achieve a speed up of around 270%, but our efficiency drops from 100% to 68%. And we can see that this line goes down, this value goes down. So although we are getting more and more speed up, we also get less and less efficient use of our resources. And this is a problem if you want to do a calculation on an HPC cluster, because you can only spend this many amount of calculation time. Well, this little figure, we can count the squares to see if the calculation is correct if you really want, but we can plot it in a more general form. This is not the same thing as in the original paper, but I'm going to post it as if it is. And here we see a graph where at the x-axis we have the number of processors. Assume for now these are the number of cores, the number of workers, the number of threads, and the speed up. And the speed up of 1 means that this is the time with 1 processor. And if we add more and more, then the speed up will go up. But what important is to note is the parallel portion. So not all parts of the program can be run in parallel. So let's assume that half of the program can be run in parallel. That means that's the blue line. It means if we have 16 processors or more, the program will never be more than twice as fast. And this was the insight by the original paper in Amdahl. And if you have 95% of the code that can be run in parallel, they can have 20% speed up maximally. But also notice how long it takes to get there. So even if you have 95% that can be run in parallel, so that means you can make it 20 times faster. Let's say you aim for 10% faster, you need around 20 processors already. So you need 20 times more processors to make it 10 times faster. That's somewhat weird. You have yeah. So leaving the theoretical part, I'm now going to walk you through the exercises. And I encourage you to first think about the answer yourself, or do these exercises yourself. But I will walk through them now. Question 1. Which of the lines in the graph of Amdahl's law corresponds with the worked out example of 16 time units? So let's take a look. I'm going to take a look at the speed up, and I'm going to look at the speed up of, well, let's take a look. I think I can speed up. So if I speed up, let's take a look at the x-axis. So I take 4, for example. 4 is in the worked out examples. Number of course 4. And with a speed up of 2.29, 2.29, that exactly matches the red dotted line. And we can maybe already intuitively feel that this line should be there, it should be this line. But let's take a look at the original computation. Like, the idea is that this is 16 time units, and this part, the green part, can be parallelized. And let's assume an infinite amount of threads or cores or workers. That would mean that this part is done in close to 0 seconds. It approaches 0 seconds. That means that it still needs to do 4 time units out of 16 to do the calculation. So it can be 4 times faster maximally, because the parallel section can be approaching 0 time units if it has infinite amount of processors. But there's always these 4 pesky time units that need to be done serial. And those you cannot get rid of. And that is what Amdahl's law is about. It's about, hey, not all code are useful enough to parallelize. And in that time there was a whole different question about why this was important. But I'm going to restrict it to this more simplified examples. In the example of 16 time units, what is the shortest amount of time that can be spent on the calculation given infinite resources? That is 4, because this is the same story I just told you. If we can put these parallel sessions all in parallel, the things we can make parallel, we do make parallel with infinite amount of cores. We always need to do these 4 time units in parallel, in series. In the example of 16 time units, what is the maximal possible speed up? Well, that goes from 16 time units to 4, so that is 4. Yeah, or 400%. Next question. And here we go more into to see if you understand what we have just discussed. Question 4. For your research project you need a lot of calculations. Each calculation takes 10 hours. How do you make optimal use of your computational resources? So imagine you have an HPC cluster. You have, on some HPC clusters, it's 10,000 core hours a month. So that means you can do 1,000 calculations each month without problems. How do you make optimal use of them? The solution is run it on a single core. There is no need to make this faster. Sure, 10 hours can feel long, but that's one evening. If you want to make optimal use of your computational resources, run it on a single core. And I know that an HPC center in Groningen calls this the poor man parallelism. Like, if you are poor, if you have a limited amount of computational resources to spend it like this. Next question. For your research project, you also have a calculation that takes 11 days. Your HPC cluster allows a calculation of at most 10 days. We're going to assume that your HPC center will not extend your job. And they will do so when you're asked. We are very cooperative here. We don't need to go against you, but I assume they are not cooperative. How do you make optimal use of your time? How do you make optimal use of your computational resources? The answer is to use 2 cores. If you well, this is a bit dependent. So if your calculation already has it built in, then run it on 2 cores. You only need to change your Slurm script, your job scheduling script, and you will lose your computational resources, but it's just adding a couple of characters, literally a couple of characters, to get this running. So that uses your time well. If you are really tight on computational resources, then the next solution is that you implement a save state in your calculation. So that means that it stops after, for example, 9 days, and then it starts another run of another 9 days, each running on a single core, and that's optimal use. But you need to program this. Also, if it's not in, you can decide, let's say there is no parallelism built in, then you can decide to add thread parallelism yourself to allow running on multiple cores. So if it's already in, use that one. If it's not in yet, if there's no thread parallelism built in, then either add a save state or add it. Whatever you think is easiest to do. Next question. Your colleague runs many jobs with a lot of cores. It is way faster, he or she states. The same colleague, however, also complains about long waiting times before his or her job starts. How would you explain this situation? Like, how would you tell the colleague what's going on? How would you explain what's going on? The answer is that this colleague probably burned up all his or her resources. Some would say wasted all his or her computational resources. So you have typically 10,000 core hours per month, and this is on UpMax, one of the HPC cluster centers. So this means this person indeed, when a job is running, when he or she gets the time to run a job, it's way faster. But the computational resources he or she has available are burned immediately. And this means you have to wait. You have to wait in the queue until it's your turn to do a calculation again. There are some HPC centers that have a so-called bonus queue. So that means if an HPC cluster is doing nothing, then those jobs are run. But most of the time you just need to wait until it's your turn again. Last question. Your colleague has also done the exercise in this session and decided to measure the same features of her code. Below you can see the plots produced by this benchmark. What seemed to be the percentage of his or her code that could be run in parallel. Alright, let's zoom out a bit that it fits on one screen. So here we have total core seconds, we have efficiency and speedup. Speedup is what we've been working with so far. And we see that the speedup goes to 1.5 typically. So you could argue that in this run, if it goes 1.5 times faster, what is this, 50% faster, that means that the speedup, that about 33% can be run in parallel. So if you say 33% would be correct. On the other hand, and that is a bit beyond what we've already been looking at, but that's why these other graphs are there. So here we see the total core seconds, and I've not discussed this yet. But this is the same calculation, and we see that the more workers we have, the more cores we have, the more time it takes for all those cores combined. And this is close to a line, close to a straight line. Also, if you look at the efficiency of the job, it drops down very, very quickly. And this dashed line is the minimally predicted efficiency. This dashed line means when you have access to multiple cores, but you still are only using one. When you still are using a single threaded code. And that is the problem here. This code, it is unknown what portion of the code can be run in parallel. Instead, this benchmark shows how it looks like if code is run in single threaded mode. So the code could theoretically be run in parallel, but it's not. Like somewhere, and this is, for example, this is a case that happened to me in Julia. In Julia, you need to specify the number of threads, the number of cores that you have available, or closely related to that, when calling, in this case, Julia. And I forgot to set that number. And if you only use, you can allocate as much cores as you want. If Julia thinks you only are allowed to use one thread, to only use one core, it won't magically look for that. So this means, so we don't know what portion of the code can be run in parallel. We do know it's run in single threaded mode. And I know this because I ran this myself in single threaded mode. Also, the plots are less clear than you may have expected. So it's very interesting that speedup actually goes up consistently. I don't know how to explain it, because Julia indeed has only one thread. It could be that if you use, but this is only guesswork. I can make up a story, but I cannot say with certainty why this is the case. Like efficiency goes up, goes down, quite similarly what is predicted, but not as deep as you would expect. Total core seconds is not a perfect straight line either. Like you see, sometimes there are hiccups up and down. And maybe it's unexpected that also in computer science results can be messier than you would expect. With that, I have now showed you about a parallel computation, in which there are three types of parallel computation, which is single-threaded, that only uses a core. There is threaded, which uses multiple threads, multiple cores to run a process, and distributed, which means this can use multiple nodes, multiple cores, multiple computers. One advantage of parallel computation is that it can speed up your calculations. Two disadvantages of parallel computation is: one, you are wasting computational resources, and two, sometimes you need to program it yourself first, and there are some unexpected errors there too. The best way how to use your computational resources effectively is to use as few cores as possible. Still, also there are other ways to use your calculation time more efficiently. For example, speeding up your code itself directly. But this session is about parallel computation, so the idea is that you're going to do this by parallelizing, but there are other techniques to make your code run faster. With this, I round off this session and I wish you a very good day. Bye!